Okay, YouTube, in this video, this is kind of a follow-up to De Moivre's theorem, in which we saw that if we have a polar form of a complex number and we raise it to a power, we could see that really what we're doing is we're raising our argument to the power that we're given here. So that would be 2 to the 6th in this particular example. And then we're multiplying our argument, which is 20 degrees, by the power. This would be stated simply De Moivre's theorem, and it just is a really convenient way for us to evaluate powers of complex numbers written in polar form. In this video, what we're going to be doing is working the other way around. And so we've referred to this in the past, as going from the left to the right here is raising to a power, but going from the right to the left, what we're going to be doing is taking an nth root of this number here. And in this case, in particular, we could say that this number 2CIS 20, that would be the 6th root of this number, but only because it is the number that when taken times itself 6 times gives us this value right here. And so we're going to say that this 2CIS 120, we'll refer to it as a complex 6th root of 64CIS 120. And what we notice here is basically that it is one of 6 distinct complex roots for 64CIS 120. But in general, if a complex number z satisfies this equation right here, then we're going to say that z, the thing that I raised to the power of n to get w, z is the nth root of w because that is the number that I can take times itself n times to get w. So the thing here is this. You're going to notice that this value here, this 2CIS 20, they mention that this is one of 6 distinct 6 roots of this number. One thing that we want to basically mention here in this video is that there are always the same number of roots as the root you are taking. And what I mean to say there is that if we're going to take a cube root, then that means that we have to have exactly 3 cube roots. And if we're going to take a 5th root, we have to have exactly 5 5th roots. And so what I want to do is kind of look at this as the opposite of raising to the power. And the reason that I want to do this is because what we're going to see happening with what we do to our argument and our modulus here are the exact inverses of what we did with powers. So when we raise a complex number to a power, we said we'll raise the argument to that power and we'll raise the modulus to that power and multiply the argument times that power right there. When working the other way around, what we're going to see is this. We're not going to raise the modulus to that power, but we're going to take that root of the modulus. And instead of multiplying the argument by that root value, we're going to divide the argument by that root value. And so you're going to see that basically listed out down here. And one thing I know is that when I show this every time, it doesn't look pretty. And so we're going to clean this up a little bit here. But let's start with this. Let's let w is this r cosine theta plus I sine theta, be a complex number in polar form, and we're not going to allow it to be 0. But we would say that w has n distinct complex nth roots given by these formulas. So again, n distinct roots if you're finding the nth root. So you have to have as many roots as the root you are taking. Okay, 7th root means you get 7 answers here. But they're given by these formulas here. So what you're going to see is that our z here, if we were to look at it as the nth root, okay, of w, so the nth root of this, let's go ahead and start with this. We'd say that the nth root of a complex number in standard form, RCIS theta. In general, what we're going to do is this. We're going to take the nth root of our r. So just like up here, when we said raise it to a power, you raise your r to that power. When we have a root of a complex number, we take the root of our modulus. And then with respect to what we do with our argument, we would say in general, we would say that last time we took n times theta. In this case, what we're going to do is we're going to take our argument and we're going to divide by n. And so this is particularly the opposite case of De Moivre's theorem. It really is an extension of De Moivre's theorem. And so what you'll see down here, written a little bit more differently than what you see I have here, and I want to make sure that you have this right here, but it's basically this. We're going to see that we get the nth root of r in either case that we take the nth root of this number, but we get cosine of theta over n, like we got here, our argument divided by n. But you'll notice on the top here they put this plus 2 pi k. And what this is doing is naming all coterminals. with the original angle here. Because we know that if we were to rotate 2 pi radians or 360 degrees and any multiple of that where k, we're going to say k is specifically starting at 0 and going up to 1 less than what the root is that we're taking, then we're going to say that really all we're doing is it's saying that our argument is being divided by n, but we have to add on multiples of a full rotation. So one thing that we want to make sure we mention down here is that k always starts at 0, okay? And k proceeds upward, proceeds up to 1 less than the root we are taking. And so what I want to do is I just want to throw this at you here and see if I can get you to understand what I mean about k. I think it's easy to look at if you have an example here. So taking a look up here, we say that there are exactly 4 fourth roots of the given complex number, and that from De Moivre's theorem for finding complex roots, we say the fourth roots of this number here are as follows. And so basically this extension of De Moivre's, we're saying that we have this number here, 16 CIS 120 degrees. Now we're asking if we were to take the fourth root of this number here, the fourth root of this number, what we would get. And so what I want everybody to recognize is that our n value here is 4. That is the n value that we're working with. And so to get this, really all we're going to do is we're going to take the fourth root of our modulus value, and then we're going to say it's CIS of 120 degrees. Now here comes the kicker. We're going to divide by n, but the one thing we want to make sure we add on top here is, because we're in degrees, we're going to say is multiples of 360 degrees k. And so I'm going to put a big box around this, because what this does is allows us to find the 4 fourth roots of this number here. So the way this is going to be done, first of all, is that we're going to simplify what's in our argument here. And the way we're going to do this is because we have a monomial divisor, just a 4 in the denominator here, then what we could do is we could take all of our terms on the top and put them individually over 4. So let's do this. We say the fourth root of 16 here. What number could we take times itself 4 times and get 16? I hope you recognize that 2 is that number here. And we say that this is really CIS of 120 degrees over 4 plus 360 degrees k over 4. And by simplify, certainly here's what I mean. We'll say 120 fourths is really 30 degrees. And we say a fourth of 360 here is 90 degrees k. So put a big box around this, because this will help us find all 4 fourth roots. So the way this is going to happen here is this, and this is where k comes in here. Once we get to this, you're in very, very good shape. As a matter of fact, all we did was we took the fourth root of 16 and we divided 120 by 4, but we made sure that we added on this multiples of 1 full rotation there. Basically what we're going to do now is we're going to substitute in values for k. So let's substitute values for k, and in terms of k, what we're going to get is this. K is equal to 0, starting at 0, and going upward until we reach 1 less than the root that we were taking. So that is to say that I'm going to stop at 3 here, and the reason why I'm going to stop at 3 is because if I were to go up to 4, basically, what if you were to plug in a 4 for k anyways? 4 times 90 would be 360, and 360 plus 30 would be over 1 full rotation. So basically, by allowing k to start at 0 and go all the way up to 1 less than the root we were taking, we're going to find all values of our roots between 0 and 2 pi, or 0 and 360. So with this number here, what we're going to get is this. We're just going to split this up. We say k equals 0 k's. What we would have gotten is 2 CIS 90 degrees plus 90 degrees times 0. In other words, we get 2 CIS 90 degrees, and I'm going to put a box around that there, because 90 degrees times 0 would cause this to drop out. Now what I want you to see is this. If we were to do k equals 1, and I usually do separate it in my work like this here using little sub areas, subsections. We say I would get 2 CIS 90 degrees plus 90 degrees times 1. And so we would really get 2 CIS 90 degrees plus 90 degrees, which is 180 degrees here. And then proceeding with this here, we could say, okay, what if we were to say k is 2? K is 2. Then what we get is this 2 CIS 90 degrees plus 90 degrees times 2. So really you can see that we're really taking our original 90 degrees and adding on 90 degrees twice, so we get 270 degrees here. And then our last fourth root, and it looks like I'm going to have some room over here to write it. We say k is 3. When k is 3, then we get 2 CIS of 90 degrees plus our 90 degrees that we had times k. So really we get 2 CIS 90 degrees plus 3 90s, which is 360, and we've all agreed that we're going to rewrite 60 degrees instead as really 0 degrees if we can help it. And so our 4 fourth roots here happen to be these 4 values that I put boxes around right here. And so one thing that I want to say about fourth roots in the complex number plane is that the interesting thing is when you graph them. Okay, let's say we were to graph these. 2 CIS 90 would mean in a 90 degree direction, let's go up 2 and draw a dot. There's 2 CIS 90. 2 CIS 180 would be rotate over to 180, and we'll go outward 2 units in that direction. We'd have 2 CIS 270, so 270s in this direction here will go 2 units in that direction. And then 2 CIS 0 would be in a 0 degree direction, go out 2 units. And so what you see is, in a circular sense, all 4 fourth roots have to be evenly spaced. Evenly spaced. And so it makes sense that we were to say that a 4 rotation evenly spaced would be increments of 90, because 360 divided 4 ways is 90 degrees per subsection. And also this evenly spaced thing, you can see that there are 4 of them in a full rotation. There should have been 4 fourth roots. So what we're going to look at here is practicing how we could find some more roots, both of numbers in standard form or rectangular form, but also numbers in polar form. So let's continue to follow up with this here. What we want to do in this next example is find all cube roots of 8. And so one thing that I want to mention here is this. This is the same thing as 8 plus 0i, okay, 8 plus 0i. And what we want to recognize is this is currently in rectangular form. Rectangular form. So if we're being asked to find all cube roots of 8, then really what we're being asked to do is find all cube roots of 8 plus 0i. Now, on a typical day, I would tell you that 8, the cube root of 8 is just 2. But what we know at this point is that all of our cube roots here, at least in terms of how many we have, there should be 3 if we're finding a cube root. So cube root means we have to have 3 roots. This is only one of our roots right here. So in order to find the other 2, what we're going to do is, first of all, we're going to convert to polar form. I'm always a big advocate of, if we're going to go into polar form, what we should do is just sketch out this number here. So 8 plus 0i, that would mean we went 8 units on our real axis here and up and down none. So with respect to what this number is in polar form, I would say that pretty simply, because this lies on a quadrant, we could easily see that our r value here is 8, okay, and that our argument here between 0 and 360 looks like it's going in a 0 degree direction. And so what we're going to do is we're going to use De Moivre's theorem here. Sorry, this is a cube root, a third root. But what we'll do is, using De Moivre's theorem or the extension of it, we could say that really what we're doing then is the cube root of 8, and then we have CIS of 0 degrees, not times 3, but divided by 3. Now the only thing we need to make sure we fill in every time at this point is plus the 360 degrees k on top. So just like last time, let's start with our cube root of 8 here, where cube root of 8 is 2. And then in terms of CIS here, CIS of what? We will do this separately. We say 0 divided by 3, or 0 degrees divided by 3, which is 0 degrees, plus 360 degrees divided by 3 is 120 degrees k. And so put a big box around this, because congratulations, this is going to help us find all of our cube roots. Now what the question is what we're going to substitute in for k. So we always certainly know that k starts at 0 here, but we're going to do k as 1 here, and because we went up to a cube root, we're going to stop at a k that's 1 less in value than the root we're taking, so we'll stop at k as 2. So in this first case, looks like we get 2 CIS. This would be 0 degrees plus 120 degrees times 0. In this next case, we get 2 CIS of 0 degrees plus 120 degrees times 1. And down here we get 2 CIS of 0 degrees plus 120 degrees times 2. So simplifying these, our very first root here is 2 CIS really of 0 degrees. So we always get that initial angle here, whatever that was here. We're going to get this for one of your answers. And for the other 2 answers here, we get 2 CIS of 0 plus 120 degrees times 1. In other words, 0 plus 120 degrees. So we get 2 CIS 120 degrees. And in this last example, we get 2 CIS of 0 plus 120 degrees times 2 really is 240 degrees. And so I'm going to put boxes around these. These are our 3 roots in polar form. And we could, if we graph these here, we could see pretty easily that, 2 CIS 0 would be 2 units in this direction here in a 0 degree direction. 2 units in a 120 degree direction might, look something like this here. We would say 2 units outward in a 120 degree direction right there. And then a 240 degree direction, 2 units out in that direction right there. Here's 240 degrees. There's this. So if we were to impose a circle around this, you could see that all 3 of our cube roots are evenly spaced about this, all 120 degrees apart within our 1 full rotation. Now the other thing we want to do is make sure that we can write these in standard form. So that is to say 2 CIS 0 here, could we write this in A plus BI form? And so certainly we can. We'd say that this is 2 cosine of 0 degrees plus I times the sine of 0 degrees. If we were to distribute here, we get 2 cosine of 0 degrees plus I times 2 times the sine of 0 degrees. So our sine and cosine values at 0 degrees here, it looks like we get a cosine value of 1 and a sine value of 0. So really what we're going to get here is 2 times the cosine of 0, which is 1, plus I times 2 times the sine of 0, which is 0. We really get 2 plus 0i, or in other words, we get 2. And so I just want to show everybody here that yes, we could have named this point just by looking at this. It was, 2 to the right, up and down, none. But this point over here, that it's 120 degrees, and we know our R value is 2. We're going to need to put in a little bit more work here in order to find A and B that go into this. So again, to convert this into standard or rectangular form, well, we're going to write it out 2 cosine of 120 degrees plus I times the sine of 120 degrees. And we'll just go ahead and distribute our 2 through and evaluate. So we get 2 cosine of 120 degrees plus I times 2 times the sine of 120 degrees. And so using a reference angle on 120 degrees, which is a 60, we could say that the cosine of 60 is a half. So we get 2 times a half. And then our sine of 120 degrees, we would get root 3 over 2. So we have I times 2 times the root 3 over 2 value here. Now, the one thing I want to make sure that I do, and I don't want to go too fast here, but basically is say, well, we evaluated the cosine and the sine at 60 degrees, but are any of them negative? And we could certainly see that cosine in the second quadrant here would be a negative value there, where our sine of 120, which was root 3 over 2, is positive. So let's go ahead and multiply these together. We'll simplify. We say 2 times a negative a half is a negative 1. Then we say plus, now I times 2 over 1 times root 3 over 2. The 2's cancel out here. We really just get root 3, and I'm going to say I is off on the side here. And so looking at this number here in standard form, we can see that we would go left 1 and up root 3 in order to get to this point here that had an angle or an argument of 120 degrees and a modulus value or a distance from the origin of being 2. So now our last value here, let's go ahead and do this one. We say 2 cosine of 240 degrees plus I times 2 times the sine of 240 degrees. We're a little bit faster on this one. 240 degrees, we could see it also has a 60 degree reference angle right here. So the nice thing about that is we're going to get cosine of 240 and the sine of 240 to come out to be the same values that we had previously, that is to say our 1/2 and root 3 over 2. Because we have the same reference angle, it's just that we'll notice that because it's in the T quadrant, the third quadrant here, and we're finding cosine and sine, those would both have negative values. And so to simplify this, we would get negative 1 here, but instead of plus root 3 over 2, we'd say multiplying these here, these cancel. We get minus root 3 times I. This would be this number here where we go left 1 and down root 3, but you can certainly see that symmetry here. So the last thing I want to do here is just this one here. Have you give this a shot on your own. And this one's a little bit simpler than the last one because all I want to do is have you find all fourth roots of this number right here and write your answers in polar form with theta in degrees. So go ahead and take your shot at this. I want you to rewrite this first of all as 16 cosine I sine of 60 degrees in an abbreviated form. But let's go ahead and write this out what we're finding here. We say the fourth root of 16 CIS of 60 degrees. So give this a shot. Unpause the video when you're done. Once you're ready to go, let's go ahead and use De Moivre's theorem that says, well, if we're going to do this here, then what we'll do is we'll just take the fourth root of our argument, and then we'll take our angle here. Instead of multiplying by n, which in this case our n is 4, we're going to divide our argument by n. So we really get 60 degrees over 4. Now the one thing we want to make sure we do is put in plus 360 degrees k. So simplifying this here, we have the fourth root of 16. Now what number we could take times itself 4 times and get 16? That would be a 2, and then we get CIS of 60 divided by 4 is 15 degrees, and 360 divided by 4, that'd be 90 degree increments here. So big fat box around this. And because we're finding the fourth root, what we need to do next is you should have evaluated for k starting at 0 and going all the way up to 1 less than our n value here. So we're going to stop just shy of 4. We're going to go to 3. And so looking at these, we'll throw this together here. We have 2 CIS of 15 degrees plus 90 degrees times 0. In our next sense, we're going to have 2 CIS of 15 degrees plus 90 degrees times 1. Here we'll have 2 CIS 15 degrees plus 90 degrees times 2. And then lastly, we have 2 CIS 15 degrees plus 90 degrees times 3. And so essentially we can see that simplifying each of these here, we could see that this first one here, and just like all of our examples, we're always ending up with the first answer that we had gotten, 2 CIS 15 degrees in this case. But basically whatever you got here to begin with, when you plug in 0 for k, this part's always going to disappear. And then afterwards what we're going to see is that when we plug in 1 for k, we're basically going to be going upward by increments of this value. So basically 2 CIS of 15 plus 90 times 1 is really 15 plus 90. We have 105 degrees here is our second fourth root. Here we get 2 CIS 15 degrees plus 180, so 195 degrees, okay, is our third fourth root. And for our last one here, we have 2 CIS 15 degrees plus 90 times 3, which in other words is 15 degrees plus 270 degrees. We get 285 degrees right here. And so not that we're required to do this, but again, I really want to emphasize this fact, essentially that if we were to sketch each of these numbers, we would say 2 units in a 15 degree direction. If I'm calling this 15 degrees right here would be there. If we said 105, that'd be 15 degrees, okay, past 90, that would be here. We say 195 is 15 degrees past 180, and then 285 is 15 degrees past 270. We can see that all 4 of our complex roots here are evenly spaced out around this circular region here. And so for the last part of this, what I want you to try is to find all cube roots of 27 and write your roots in rectangular form. So again, this is just another example that looked like this first one here that we did, this one here where we found all cube roots of 8. What I want you to try is all cube roots of 27 using that as an example. Go ahead and give it a shot. When you're ready to see the solutions, go ahead and hit play on your video here. Looking at 27, what we did in the last instance, we said if we wanted to find the cube root of 27, you know, we would usually get 3, but we know that we have to have 3 of them. This is only one. This is only one cube root. Okay, we need 3. So essentially what we're going to do here is, again, we're going to write this as a complex number in standard form. So we would say the cube root of 27 would be really the cube root of 27 plus 0i. And then what we're going to do is we're just going to go rewrite this into RCIS theta form. So RCIS theta form so that we could use De Moivre's theorem and find all cube roots of this. So in terms of where 27 plus 0i would be, I hope you can see that it would be 27 units to the right and up and down none. So with respect to this number here, the nice thing about it is it's purely real, which means its RCIS theta form is very easy to find. It's 27 units in a 0 degree direction here. And so to use De Moivre's, again, what we'll do is we'll start by taking the cube root of our argument, and then we say CIS of our argument 0 here, divided by our 3, not multiplied by 3. And of course, lastly, making sure that we fill in this right here. So because we're finding cube roots, let's go ahead and do our cube root of 27. We get 3. And simplify this value here, we say 0 divided by 3 is 0 degrees, and 360 divided by 3 is 120 degrees. Essentially what we get is this right here. So big fat box, we're going to do this for k is 0, k is 1, and k is 2. So with k is 0, I'm going to go a little bit faster in this example here. We get really 3 CIS, and we would have 0 plus 120 degrees times 0. Really, we just get that 0 right there. So for our first cube root, we get 3 CIS 0. When k is equal to 1, okay, we would get 3 CIS 0 plus 120 degrees times 1. So in other words, we would get 3 CIS 0 plus 120 degrees, in other words, 120 degrees. So I'll put a box around this. And then for K equals 2 here, we would say we get 3 CIS of 0 plus 2 120s. So in other words, 240 degrees there. I'm going to fix that degree symbol, make it a little bit smaller. Whoops. And so these are our 3 cube roots here. What we want to do is actually write these in rectangular form. So one thing you'll want to do before you piece out of this video is essentially say, well, okay, well then really what this would be is 3 cosine of 0 degrees plus I sine of 0 degrees. Here we get 3 cosine, let me try that again here, cosine of 120 degrees plus I sine of 120 degrees. And then here we get 3 cosine of 240 degrees plus I times the sine of 240 degrees. So to evaluate this first one here, we'd say really we have 3 cosine of theta plus I, 3 sine of theta, which in this case our theta is 0. So remember that our cosine value at 0 is 1 and our sine value at 0 is 0. We get 3 times really 1 here plus I times 3 times 0. So in other words, this cancels out. We really get left with 3. And so in rectangular form, here's one of our cube roots. But really, that's still the same thing as what we see here in polar form, 3 units in a 0 degree direction. Now, this other one here, if we wanted in rectangular form, that would be 120 degrees going 3 units outward from there. And I guess I shouldn't use my unit circle over here to do this picture. But we would say that if we're going to evaluate for 120 degrees right here, the cosine and the sine of that angle, then really what we want to use is the reference angle. And so that reference angle being 60, we could say that really we'll use that instead. So we get I times the 3 times the sine of 120 degrees. We get the cosine of 120 is the same as the cosine of 60, and the cosine of 60 is a half. And also because our angle terminated in the second quadrant, we'd say this is a negative value since cosine is negative in the second quadrant. And then over here we get I times 3 times the sine of 120, which would have to be root 3 over 2 at a 60, except for our sine value here in the positive, or in the second quadrant is positive. So to simplify this here, we'd say multiplying straight across, looks like we get a negative 3 over 2 here, negative 3 halves, plus now simplifying this, we don't get anything to cancel, but what we do get is we get 3 root 3 over 2 times I right there. And so this would be the rectangular form of this number that we see right here. And then lastly, our 240 degree angle. My favorite thing about 240 is that it also has a reference angle of 60 degrees. And so in terms of the values we get here, we're going to get really the same values numerically. We say 3I sine of 240. Sorry, I messed up my I and my 3's order there. But basically, we're going to get 3 cosine of 240, which is really the cosine of 60, which is a half, but negative because we're in the third quadrant here. Plus now 3 times I times the sine of 240, which is root 3 over 2, because it has a 60 degree reference angle, but is also negative because we're in the third quadrant where the only thing positive is tangent. So simplifying this, we get negative 3 halves this time, but instead we get minus 3 root 3 over 2 times I. And so you can see that with this number here, we would have to go left and down to get to this, but our rectangular form of this number supports this conclusion. We go left 1.5 and then down 3 root 3 over 2 to get to that number there. Cheers.